Okay, guys, so we start seeing a little bit about IPSec transform sets, as they are called in Cisco iOS configuration, or just transforms in RFCs. Also, each of them have a different transform type, so depending on the type of algorithm that we're referring to. So by the way, we have 4 cryptographic algorithms that are going to be negotiated during those IKE security associations. So one of them is an actual encryption algorithm. So that's the algorithm that's going to protect our data, to encrypt our data. That could be DES, 3DES, or AES. By the way, the first 2 are older ones. You should use AES, which is a newer one. Then we have an integrity protection algorithm. They are called hashed message authentication codes, or keyed hashed message authentication codes, because they are created with a key plus an MD5 or SHA algorithms, for instance. And this is to create a hash with some immutable data, so to make sure that information hasn't changed during transmission. Then we have our Diffie-Hellman group. This is a great mathematical function that allows us to create private keys or secret keys, exchanging public key, for instance, on the internet. We're going to see that a little bit how they work. And by the way, these are renamed as key exchanges from RFC 9370. So the idea is that we can use a different algorithm, not just a Diffie-Hellman, to do this. And finally, this pseudo-random function that is going to be also negotiated during those security associations, basically to make sure that those keys that we negotiate are unique and just for that specific session. So we make a brief stop here on the Diffie-Hellman group. This is how it works. Here you have an example. You can see this in Wikipedia, but I think it's nice, to check a little bit how this works. So basically, this is a way, for 2 different devices or 2 different people arrive to the same secret key, exchanging some public information. Basically, you can see, you can check later or read how all the mathematical function, but basically it's exchanging these parameters here, this group and this modulus operation. And basically you see how after the exchange and making these mathematical functions, they arrive to this secret key, without exchanging that specific key, but exchanging something else, right? So this is very nice and a very nice algorithm for cryptography and to protect our data, and basically to create our keys, right? And finally, the second step we're going to do is with the security associations. Basically, security associations database, which is SAD. And this is just for you to know that maybe when we run some commands in Cisco iOS, we're going to see a lot of information. So all this information is basically mandatory, when we are developing, an IPSec, a device running IPSec. So basically, I'm not going to go over all of them, but for you to have an idea, most important ones are this security parameter index. So basically, this identifies that security association. Then, of course, the algorithm that we're going to use for encryption, sequence number. This is going to help us, to avoid those attacks, those reply attacks that we were mentioning in the beginning. We can also use an anti-reply window, which is just kind of the same. MTU functions, to check that the MTUs are correct. Well, of course, tunnel, source and IP and destination addresses in case that we're doing tunneling mode. So this is just for you to know that this is all the information that we're going to see in a security association database when we deploy IPSec in the device. Okay, so now we touch base with our 2 protocols, IPSec AH and IPSec ESP. So we start with the authentication header. This is protocol 51, right? Depending on the protocol that we are using. For IPv4, it's going to be on the header. In IPv6, it's going to be on the next header section. And these are the services that authentication header is going to provide for us. So access control, integrity, data origin authentication, and anti-reply features as optional. So you see here in the header some of those parameters that we saw in the security association. For instance, the SPI, security parameter index, the sequence number fields, right, to sequence all the IPSec packets, and this integrity check value, right, that hash that is going to be calculated with information of the packet to make sure that that information hasn't changed during transport, right? The other end is going to calculate the same, and of course they have to match. So here you have more detailed view of the authentication header packets, right? Kind of before and after view, and also how they look like depending if you're using transport mode or tunnel mode. I have to move myself a little bit so you can see the IPv6 here. So first of all, if we start here on the transport mode for IPv4, so you see here, this is how the packet looks like, at the beginning without before applying authentication header. And now here, this is the packet, after applying authentication header in transport mode. So remember, in transport mode, we do not put that into a tunnel. So the original IP header, original source and destination are going to be kept the same. And here we put that information that we saw previously, that authentication header information. So, and you see here these mutable fields and immutable fields, right? And this is the authentication except for mutable fields. So that means that all the information that is immutable, right, is going to be hashed, right? And that's basically the information that authentication header is going to protect, right? The information that is mutable, so that means that the changes across the transport of the packet cannot be, secured by authentication header, just information that is immutable. Remember that in this case, we are not encrypting, the information. So the information is still in clear text, but we are, creating a hash. We are authenticating that information to make sure that that information arrived unchanged. And finally, I'm just moving a little bit myself. You see here, in this case, the same concept, but in tunnel mode. So in this case, we do have a new IP before header, also new source and destination addresses. So in this case, yes, the original IP header is also part of the immutable field. So in this case, we're going to authenticate also the source and destination portions of the packet. In the case of IPv6, right, pretty much the same, just of course taking into account the differences between the IPv4 and IPv6 headers, but the idea is the same, right? So in this case, we don't change the original IP header. We just put after these options here the authentication header, and these immutable fields are the ones that are going to be protected by authentication header. And in the case of tunnel mode, right, we create our new IPv6 header, and the authentication header is put after these extended headers, right, if present. And now the original IPv6 header is also protected. Okay, and here we are with our last protocol, the IPSec ESP, or encapsulation security payload. Here you see, right, that in addition to what AH provides, it also provides confidentiality. Why? Because it encrypts, the actual payload, the actual data that we're sending across that insecure channel. So you see here, right, that we not only have that integrity check value, right, but we also have our payload data, right, which is in the part here, which is the confidentiality part, right, covered. So that means that gets encrypted, right? And this is the integrity part covered. So that means that it provides integrity for SPI and sequence numbers, and it also provides confidentiality for our payload data. And the same slide, but now for ESP and also for IPv4 and IPv6. So how our IP headers look like, before and after we use ESP, to protect our information. Also, for transport mode and tunnel mode. So you see here for IPv4, so the same concept, but now instead of that AH header, we are adding our ESP header. In this case, it's transport mode, so our original IP header is not changed. And you see here that after so from the TCP portion, so for the segment portion onwards, this information, so this is what gets encrypted, so that's where we have that confidentiality. And the ESP header is also protected for integrity, so that means that hash also gets data from the ESP header, so we basically make sure that it is not changed, during transmission. And the same goes here, but in the tunnel mode, where we also the same concept, but now we put our new IPv4 header in this case with our tunnel source and IP source and destination IPs. And in this case, this is you see in this case the full IPv4 header from the original packet also gets encrypted, right? And from ESP header, into the ESP trailer gets the integrity checks. And the same goes for IPv6, so the same criteria, but of course taking into account that the IPv6 packet format, right? So you see basically the differences between the transport mode and the tunnel mode. In the tunnel mode, we have our new IP header, and these sections here are the ones that get encrypted and integrity checked, or in this case for the tunnel mode, those that the full IPv6 original IPv6 packet gets encrypted, and the ESP portion also protected by integrity. And last but not least, last stop before we move into our lab, I just wanted to point out this NAT traversal feature or option that we have. Here I have also to move a little bit so you can read everything. So basically, the problem that we have when we are using IPSec between devices that are providing NAT services is that, as you saw, right, to get that integrity checks, we have to make sure that some of the packet information gets, it's not mutable, right? So gets the same, from source to destination, and the NAT protocols usually need to change, or need to adapt the protocols to make sure that they can traverse, through NAT devices. So that's why the IETF people say, okay, instead of breaking, of course, the security of the protocol, what we're going to do is just encapsulate our IPsec packets into UDP, right? So why just to use the UDP ports and the UDP headers to provide to NAT that information, when we have NAT devices in the middle. So basically, this can be checked, either by just initiating the information instead of on the port 500, which is the standard protocol for IPsec. We start our communication on port 4500. Or we can use, if the devices support that, the NAT detection payloads, where we basically create hashing, with the source and destinations. And if those are different, from that hash that we did, okay, so we basically are telling that our source and destination changed. So most probably there is a NAT device in the middle changing, our source and or destination IP addresses.